NENOMATICA, where mathematics meets YouTube excellence. The eighth law of power. Here's our example. We need to prove that the following equality is true. To start, let's rewrite each number in the equation using its prime factorization. First, let's rewrite 20 as 2 squared times 5. Now, let's rewrite 8 as 2 cubed. Let's also write 25 as 5 squared. Finally, let's express 10 as 2 times 5. Now, let's use the power of a power property which states that when we have a power raised to another power, we multiply the exponents. We'll apply this to each term in our expression. Let's multiply out the expressions in each exponent. In the numerator, 2 times 2 plus 3 equals 4 plus 6. For 5, we have 1 times 2 plus 3, which is 2 plus 3. For 2 cubed to the power of a minus 1, we get 3 times a minus 1, which equals 3 a minus 3. Now, let's combine the like terms. We can combine all the terms with the same base. For the base 2 in the numerator, we have 4 a plus 6 and 3 a minus 3. For the base 5 in the numerator, we have 2 a plus 3. In the denominator, we have 5 to the power of 6 a minus 2 and negative 4 plus 5. And we have 2 to the power of negative 4 plus 5. Let's add up the exponents for each base. For the base 2 in the numerator, for a plus 6 plus 3 a minus 3 equals 7 a plus 3. For the base 5 in the denominator, 6 a minus 2 plus negative 4 a plus 5 simplifies to 2 a plus 3. Now we can cancel out common factors. We notice that 5 to the power of 2 a plus 3 appears in both the numerator and denominator, so these cancel out. When dividing exponential expressions with the same base, we subtract the exponents. So now we have 2 to the power of 7 a plus 3 minus negative 4 a plus 5. Let's simplify the expression in the exponent. We have 7 a plus 3 minus the quantity negative 4 a plus 5. Since we're subtracting a negative 4a, that becomes positive 4a. And subtracting positive 5 gives us negative 5. So we have 7 a plus 3 plus 4 a minus 5, which equals 11 a minus 2. We need to show that the left side of equals 5 raised to the power of 55. Let's start by simplifying the denominator. We notice that 5 to the power of negative 13 is a common factor in both terms. Now, we can subtract in the parentheses to get 5 times 5 to the power of negative 13. Next, we'll convert 0.008 to a fraction. This is 8 divided by 1,000. Now, we'll apply the negative exponent rule. When a fraction is raised to a negative power, it's equivalent to flipping the fraction and making the exponent positive. We can rewrite 25 as 5 squared. We can apply the power of a power rule to calculate 5 squared, raised to the power of 11. This becomes 5 to the power of 22. Now, let's calculate 1,000 divided by 8. 1,000 divided by 8 equals 125. We can also express 125 as 5 cubed. Using the power of a power rule again, 5 cubed raised to the power of 7 equals 5 to the power of 21. Now, in the numerator, we can combine 5 to the power of 21 and 5 to the power of 22 by adding the exponents. This gives us 5 to the power of 43. In the denominator, we can rewrite 5 times 5 to the power of negative 13 as 5 to the power of 1 plus negative 13, which equals 5 to the power of negative 12. Using the quotient rule for exponents, we get 5 to the power of 43 minus negative 12, which is 5 to the power of 55. Therefore, we verified that the left side of our deed equal to 5 to the power of 55, which 4 to the negative 7 power divided by 36 to the negative 7 power equals 3 to the 5th power. First, let's apply the rules of exponents to simplify this expression. When we divide numbers with the same exponent, we can divide their bases and keep the exponent the same. So 4 to the negative 7 divided by 36 to the negative 7 equals 4 divided by 36, all to the negative 7 power. Next, let's simplify the fraction in the numerator. For divided by 36 equals 1/9. Now, let's handle the negative exponent. A negative exponent means we take the reciprocal of the base and change the sign of the exponent. So 1/9 to the negative 7 power becomes 9 to the 7th power. To make further progress, let's express 9 and 27 in terms of powers of 3. We have 9 equals 3 squared and 27 equals 3 cubed. When we have a power raised to another power, we multiply the exponents. So 3 squared raised to the 7th power equals 3 to the 14th power. Similarly, 3 cubed raised to the 5th power equals 3 to the 15th power. In the denominator, we have a product of powers with the same base. When multiplying powers with the same base, we add the exponents. So 3 to the 15th power times 3 to the negative 6th power equals 3 to the 15 minus 6th power, which is 3 to the 9th power. Now, when we divide powers with the same base, we subtract the exponents. So 3 to the 14th power divided by 3 to the 9th power equals 3 to the 14 minus 9 power, which is 3 to the 5th power. Simplifying, we get 3 to the 5th power equals 3 to the 5th power. We need to show that the fraction with negative 8 raised to the power of 20 times 2 to the power of negative 7 in the numerator and 0.25 raised to the power of negative 3 times negative 4 cubed in the denominator is equal to negative 2 raised to the power of 41. Let's solve this step by step. First, we'll rewrite all the terms using their prime factorizations. Negative 8 can be written as negative 1 times 2 cubed. 0.25 is 1/4, which is 25 over 100, and negative 4 equals negative 1 times 2 squared. Now, let's rewrite our expression by substituting these factorizations. In the numerator, negative 8 to the power of 20 becomes negative 1 to the power of 20 times 2 cubed, all raised to the power of 20, multiplied by 2 to the power of negative 7. In the denominator, we have 25 over 100, all raised to the power of negative 3, multiplied by negative 1 cubed times 2 squared, all cubed. Now, let's apply the power of a power rule, which states that a to the power of m, all raised to the power of n, equals a to the power of m times n. Using this rule, 2 cubed to the power of 20 becomes 2 to the power of 60. Also, negative 1 to the power of 20 equals positive 1, since negative 1 raised to an even power is always positive 1. Let's simplify the numerator by combining the powers of 2. 2 to the 60 times 2 to the negative 7 equals 2 to the power of 60 minus 7, which is 2 to the power of 53. Now, let's work on simplifying the denominator. First, 25 over 100 equals 1/4, or 2 to the negative 2nd power. So, 1/4 raised to the power of negative 3 equals 4 cubed, or 2 to the power of 6. Negative 1 cubed equals negative 1. And 2 squared, all cubed, equals 2 to the power of 6. Let's substitute these simplified terms into our expression. Now our expression becomes 2 to the 53 divided by 2 to the 6th power times negative 1 times 2 to the 6th power. Let's combine the powers of 2 in the denominator. 2 to the 6th times 2 to the 6th equals 2 to the 12th. Now, let's simplify the fraction. When dividing powers with the same base, we subtract the exponents. So, 2 to the 53 divided by 2 to the 12th equals 2 to the 53 minus 12, which is 2 to the 41. And 1 divided by negative 1 equals negative 1. Therefore, our final answer is negative 2 to the 41. Let's look at our example. We need to verify the following equality. 2 raised to the power of 17 divided by 0.2 raised to the power of 17 divided by 10 to the power of 11 divided by 0.01 to the power of negative 4 equals 10 to the power of 14. 2 to the power of 17 divided by 0.2 to the power of 17. First, let's rewrite 0.2 as a fraction. 0.2 equals 2 divided by 10, or 2 times 10 to the negative 1. Now, we can rewrite the division as 2 to the 17 divided by the quantity 2 times 10 to the negative 1, all raised to the 17th power. Using the property that when a product is raised to a power, we can distribute the exponent to each factor, we get 2 to the 17 divided by the product of 2 to the 17 and 10 to the negative 17. This simplifies to 1 divided by 10 to the negative 17, or 10 to the positive 17. Now, let's look at the denominator. 10 to the 11th divided by 0.01 to the negative 4th power. First, let's convert 0.01 to scientific notation. 0.01 equals 10 to the negative 2. So our denominator becomes 10 to the 11th power divided by 10 to the negative 2, all raised to the negative 4th power. Let's simplify the denominator further. When a number raised to a power is itself raised to another power, we multiply the exponents. So 10 to the negative 2 raised to the negative 4th power equals 10 to the negative 2 times negative 4, which is 10 to the positive 8. Now our denominator is 10 to the 11th divided by 10 to the 8th, which equals 10 to the 11th minus 8th, which is 10 to the 3rd power. Now we can combine our simplified numerator and denominator. We have 10 to the 17th power divided by 10 to the 3rd power. Using the exponent division rule, this equals 10 to the 17th minus 3rd power, which gives us 10 to the 14th power, or 10 with 14 zeros following it. The first step is to recognize that we can rewrite these decimals as fractions with powers. This will make our work easier. Let's analyze how the original decimals were converted in the next step. The decimals have been rewritten in a more recognizable form where we can see their relationship more clearly. In this step, we multiply the values inside the parentheses. Notice that in the numerator, we have 0.3 cubed times 0.2 cubed times 0.4 cubed. And in the denominator, we have 0.012 cubed. Now, we can multiply the values inside the parentheses in the numerator. 0.3 times 0.2 times 0.4 equals 0.024. Now, we can simplify the fraction by dividing numerator and denominator. We have 0.024 divided by 0.012, which equals 2. Let's calculate the fraction 0.024 divided by 0.012. This equals 2. Finally, we can compute 2 cubed, which equals 8. But looking at our original equation, we needed to show that the expression equals 2 cubed. This means our answer is correct, and we have verified the equality. So, we've successfully verified that the expression on the left is indeed equal to 2 cubed. The key to solving this problem was recognizing how to rewrite the decimals and carefully applying the properties of exponents. To solve this problem, we'll first decompose the numbers into their prime factors. This will allow us to simplify the expression more effectively. Now, let's apply the power of a power rule. When we have an expression like a to the power of m raised to the power of n, this equals a raised to the power of m times n. Now let's combine like terms in the numerator and denominator. We can simplify by adding exponents for terms with the same base. Now we can cancel out common factors in the numerator and denominator. Notice that 3 to the power of 22 and 5 to the power of 11 appear in both the numerator and denominator, so they cancel out. Next, we apply the quotient rule for exponents. When dividing powers with the same base, we subtract the exponents. So 2 to the power of 23 divided by 2 to the power of 77 equals 2 to the power of 23 minus 77. So we verified that the left side of the equals 2 to the power of negative 54, which matches the right side of this. Confirms that our solution is correct. In this problem, we used several important properties of exponents. First, we decomposed numbers into prime factors. Then, we applied the power of a power rule, which states that a to the m to the power of n equals a to the power of m times n. We also used the product rule, which states that a to the power of m times a to the power of n equals a to the power of m plus n. Finally, we applied the quotient rule, which states that a to the power of m divided by a to the power of n equals a to the power of m minus n. These rules are essential when working with expressions involving exponents and different bases. Welcome to this algebra video where we'll prove an algebraic equality by working through a step-by-step solution. Let's start with our example. We need to prove the following equality. The left side contains a fraction with a product of powers in the numerator and denominator, and the right side shows this expression is equal to the quantity a times b times c all raised to the 6th power. Let's begin solving this problem. First, let's simplify the expression inside the parentheses on the left side. We'll rewrite terms to make the calculations easier. Notice that 2 appears twice, and 3 appears multiple times in the expression. We can rewrite 2 to the power of 3 as 2 times 2 to the power of negative 1. Similarly, we can rewrite 3 to the power of 3 as 3 times 3 to the power of negative 1. Now, let's simplify the expressions by grouping like terms. We can express 2 to the power of 3 times 2 to the power of negative 1 as 2 to the power of 2. Similarly, 3 to the power of 3 times 3 to the power of negative 1 is 3 to the power of 2. We can also simplify the terms with a, b, and c. Let's further simplify the expression. We can see that 2 squared and 3 squared appear in both the numerator and denominator, so they cancel out, leaving us with ab and c to the power of negative 2 in the numerator. Now, we need to apply the power to a power rule. We have ab and c each raised to the power of negative 2, and then the entire expression is raised to the power of negative 3. When we have a power raised to another power, we multiply the exponents. So we have a, b, and c each raised to the power of negative 2 times negative 3, which equals positive 6. Let's continue simplifying. Negative 2 times negative 3 equals positive 6. So we have a, b, and c each raised to the power of 6. For our final step, we need to use the rule for distributing exponents. When a product is raised to a power, each factor is raised to that power. So a to the 6th times b to the 6th times c to the 6th equals the product of a times b times c, all raised to the 6th power. And with that, we've successfully proven the equality. We've worked through several algebraic steps, including 1. Breaking down exponents, 2. Combining like terms, 3. Canceling common factors, 4. Applying the power to a power rule, 5. Using the distributive property of exponents. These are powerful tools in algebra that help us simplify complex expressions. Welcome to our video on working with exponential expressions. Today, we'll verify an algebraic equality involving fractions with exponential terms. Let's look at our example. Let's start by rearranging the terms in the numerator and denominator. We'll rewrite the expression to group similar bases together. Now we can apply the product rule of exponents to combine terms with the same base. Remember, when multiplying terms with the same base, we add the exponents. Let's simplify the exponents and constants. We have a to the negative 1, b to the negative 1, and c to the negative 1. For the constants, we have 15 times 3 times 4 in the numerator and 12 times 3 times 5 in the denominator. Now we can simplify the constants. Notice that we have 180 in both the numerator and denominator, so they cancel out. Next, let's apply the power rule for exponents. When we raise a product to a power, we raise each factor to that power. Now we'll apply another rule. When raising a power to another power, we multiply the exponents. Finally, we can rewrite this as a single expression by using the product rule in reverse. When we have terms with the same exponent, we can write it as a product raised to that exponent. And there we have it. We've proven that the original expression is equal to a times b times c raised to the negative 6th power. This proof demonstrates how to work with complex exponential expressions by applying various exponent rules step by step. Welcome to this video where we'll prove an algebraic equality using exponent properties. Let's look at our example. We need to prove that the expression a to the power m plus n times a to the power m minus n times a to the power negative m, all over b to the power m minus n times b to the power m plus n times b to the power negative m equals over b raised to the power m. Let's solve this step by step. First, we'll focus on simplifying the numerator, using the property that when we multiply exponential terms with the same base, we add the exponents. Now, let's work on the numerator. We add the exponents m plus n minus n plus negative m. When we add these together, we get m plus n minus n plus negative m. Let's simplify the expression in the numerator. We have m plus n minus n plus negative m. First, let's group m plus m, which gives us 2m. Then we have plus n minus n, which equals 0. Finally, we add negative m, giving us 2m minus m, which equals m. Now, let's apply the same approach to the denominator. We'll add the exponents m minus n plus negative m. Let's simplify the expression in the denominator. We have m minus n plus negative m. First, we group m plus m, which gives us 2m. Then we have minus n plus n, which equals 0. Finally, we add negative m, giving us 2m minus m, which equals m. Now our expression has simplified to a to the power m over b to the power m. Using the property of quotient with same exponent, we can rewrite this as a over b raised to the power m. Let's start with our problem. We need to prove the following equality. I'll solve this step by step using the properties of exponents. First, let's simplify each of the fractions inside the parentheses by applying the division rule for exponents. Let's begin by simplifying the first fraction. We have a to the power of m plus n divided by a to the power of m minus n. Using the division rule for exponents, we can subtract the exponents. So this becomes a to the power of m plus n minus the quantity m minus n, which simplifies to a to the power of 2n. Next, let's simplify the expressions in the exponents. In the first fraction, m plus n minus the quantity m minus n equals m plus n minus m plus n, which gives us 2n. Similarly for the denominator of the first fraction. For the second fraction, let's combine the exponents in the numerator. We have b to the power of n minus m plus n plus m. This simplifies to b to the power of 2n. Similarly, in the denominator, we have c to the power of n plus m plus n minus m, which also simplifies to c to the power of 2n. Now, we have a simpler expression. The first fraction is a to the power of 2n divided by b to the power of 2n. The second fraction is b to the power of 2n divided by c to the power of 2n. Now, let's multiply these two fractions. When we multiply fractions, we multiply the numerators and multiply the denominators. We can simplify this expression further. Notice that we have b to the power of 2n in both the numerator and denominator, so these cancel out. This gives us a to the power of 2n divided by c to the power of 2n. Using another property of exponents, we can rewrite this as the power of a fraction. We have a to the power of 2n divided by c to the power of 2n, which equals the fraction of over c raised to the power of 2n. And there we have it. We've proven that the original expression equals over c to the power of 2n, which matches our right-hand side. Therefore, the given equality is indeed true. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.